Why does glycogen utilization, sorry, that's my pet goat, increase with increasing exercise intensity? Find out why in this video.
Here you can see the participant exercise at a low intensity. Here, the AMP inflow is relatively low and exercise is easy. Now, let's see what adding some weight does to his AMP inflow. Here he is exercising at a high intensity, his AMP inflow is drastically increased, and glycogen utilization is also drastically increased.
How does this increase glycogen utilization?
We hypothesize that ATP mass is increasing as exercise intensity increases. With increasing exercise intensity, we know there to be a higher ATP demand, and thus higher ATP breakdown. When ATP is broken down, this leads to an increase in inflow for AMP. And yeah, we're pretty amped about that. As you can see from this illustration, increases in AMP activate phos kinase, which in turn phosphorylates glycogen phosphorylase, or phos. Phos is in turn post-transformationally modified by our high AMP and inorganic phosphate. Referring back to our inflow-outflow model, phos activity is our conductance for glycogen outflow. Since phos is now more active, we see a greater outflow of glycogen from our mass, aka increased glycogen utilization as exercise intensity increases.
Now to further help demonstrate this, we will use a water bottle.
This is an example of inflow equaling outflow. Here you can see that the mass, AMP, in our model is relatively the same and steady. This was seen when he was at low intensity exercise. Outflow is way greater than inflow, uncontrollable. This is what we hypothesize is happening when you increase exercise intensity. Inflow is greater than outflow, thus you get an increase in the pool of AMP and eventually increase in glycogen utilization.
But, is there proof?
In a study by Howlett and colleagues, 7 healthy participants with a mean age of 22 participated in a crossover design study that investigated the transformational control of skeletal muscle glycogen phosphorylase at 3 different power outputs, these being 35%, 65%, and 90% of maximal oxygen uptake. Providing evidence to our hypothesis, AMP and ADP were shown to increase with increasing exercise intensities. In accordance with our model for inflow and outflow of AMP and glycogen pools, the increased inflow for AMP shown in this study would have led to an increase in glycogen utilization or outflow for each increase in exercise intensity.